Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to show you a small but useful circuit that can basically tell us if a battery is still good enough or if it's consumed. The simplest form of seeing if a battery-powered device is still has enough battery in it or not, especially when we are building the device ourselves, is to basically have a LED placed in series with a resistor across the entire power supply, which is, well, a battery in this case. And the idea is that as the voltage drops, because the battery gets consumed, the LED will start to shine less bright and less bright and less bright, and at some point it should almost stop it shining. The problem with that, there are actually two problems. One is that we are constantly drawing some milliamps out of the battery just to see that the battery is still good enough. Obviously, that's a bit stupid. The second problem is that we don't get a clear result. We don't get a clear confirmation about whether the battery is still good enough or not, because LEDs can shine light even at considerably lower currents, as I will show you in this video, in the various pictures I took from my experiments. So this way it's not such a good idea to see if the battery is still good enough. A better idea would be to have a sort of circuit that basically turns on a LED only when the voltage from the battery has gone down a certain level. In other words, when the battery is depleted too much, and the LED stays turned off while the battery still has enough juice in it. Okay? So for that we need a little bit more complex circuit. Not very complex, but a little bit more than just a resistor. Okay? And that's what we have here, that's what I'm presenting to you, and that's what I've tested on a breadboard earlier. We are using two NPN transistors, bipolar transistors. The first one, T10, is the one that switches the LED on and off, and the second one, T11 in this schematic, is the one that switches the first transistor on and off based on the voltage of the battery. In my case, I want to know when a 9-volt battery drops at or below 6 volts, because I need to power a certain circuit that can work from 6 volts upwards, and it cannot work properly under 6 volts. So that's my threshold value. Okay, so I want to have this LED turned off while the battery has 6 volts or more, and I want this LED to start turning on and start shining light when the battery goes below 6 volts, at least approximately. Okay, so needless to say, when we have to design such a circuit which operates from a battery, we need to make sure that it draws as little current as possible, okay, because we don't want to put too much stress on the battery just for such a small feature. So we have our LED, we have a limiting resistor, current limiting resistor, R37 in this case, which I chose it for 820 ohms, because, well, if the LED needs about 2 volts and it needs to turn on at 6 volts, then the remaining voltage across the resistor and the transistor is, well, the difference, 4 volts. 4 divided by 5 milliamps is about 800 ohms. Okay, so I choose an 820 ohm resistor, the next standard value. We are going to assume that T10 gets into full saturation and that the collector emitter voltage will be basically negligible. Now, this transistor by itself through the R36 resistor will get turned on and will stay turned on constantly if it wouldn't have the rest of the components. Okay, R36 is calculated based on the minimum transistor beta coefficient and the current that we need to push into our LED. And I came to the conclusion that for a minimum of 200 beta, we need about 220 kilo ohm resistance here. Not bigger, because bigger would mean that T10 wouldn't have enough current in the base to open itself enough to, you know, allow enough current for the LED to flow through. So 220 kilo ohm is pretty good because the so-called quiescent current that we get is relatively small. Now, since T10 would basically be constantly turned on and would never turn off, we need to do something to turn it off. And for that, it's quite simple. We just need an extra transistor with its collector connected to the base of the first transistor, and the emitters should be in common, so that when this transistor opens, T11 in my case, it will basically pull the base of the T10 transistor down to the ground and it will essentially turn it off. And for T11 we can actually apply a fraction of the input voltage, so basically a fraction of the voltage that we get from our battery. The idea is that if we calculate R38 and R39 in a right way, and it's not just a matter of calculation, we will have to also make some experiments on the breadboard, because we cannot properly calculate only strictly at a mathematical level, okay? But if we choose R38 and R39 right, then we will get enough voltage to open T11 and this one will close T10 only when the voltage of the battery will go above a certain threshold. And when the voltage drops down, then T11 will not have enough base emitter voltage. It will remain closed, which means that T10 will be able to conduct and turn on the LED. Okay? And that's the whole philosophy of it. It's not rocket science, it's quite simple. We couldn't have done this with a single transistor because, again, we need to have this reverse phenomenon going on. When the voltage is high enough, T10 must be closed, and when the voltage is low, T10 must be allowed to open. So for that we needed the second transistor. Okay. Now, since the collector current of T11 will be basically the base current of T10, because it's essentially the same one that we get from R36, the base current of T11 will need to be a lot smaller. So R38 and R39 can have ridiculously high values. Okay. In my case, I chose a 1 megohm resistor in series with 100 kilo ohm because in practice I've seen that that suits me best. For triggering this whole circuit around 6 volts, I needed these values. Now, I haven't measured them precisely to know that I have a precise 1 megohm and precise 100 kilo ohm. I just picked 2 resistors from, you know, my bag of resistors of each value. and they happen to be the right ones. So that being said, let me show you with a few pictures how this circuit operates and what are the results. So we have here the circuit on the breadboard on the right side of the screen. You can also see the red LED here that in this picture it's shining light. The yellow multimeter on the left shows the voltage across the entire circuit. The black smaller multimeter shows the current through the entire circuit. And sometimes it will show the current in milliamps, sometimes in microamps. I will tell you each and every time, but basically you have to pay attention to where this range selector is positioned. So for me, this circuit, since I wanted it to have this threshold at 6 volts or around 6 volts, I managed to get it somewhere between 6.1 and 6.2 volts, which is nice because it's a fairly small range of voltages inside of which, you know, the LED starts to open or close. So that's good. That's good because we don't want a very big range and to have multiple levels of light intensity for our LED. We want our LED ideally to just be fully open or fully closed. Okay, so shine light or just remain dark. And we get pretty close to that results here. So for 6.1 volts, we see that the voltage is too low, so the entire circuit allows the LED to shine enough light for us to see it. For 6.2 volts, however, the voltage is high enough, so the LED turns off. Okay. For 6.1 volts, the whole circuit was drawing 1.5 milliamps. This is a 5 milliamp LED, so 1.5 milliamps is not gonna make it shine as bright as usual. However, we see that it's still good enough for us to see basically that the battery is too low. Okay. And when the whole circuit is having the LED turned off, we have a total current of 33 microamps that's drawn from this circuit. So that's perfect. It means that it's not gonna put too much stress on the battery. It's not gonna consume too much current by itself, because after all, it's not supposed to, you know, it's supposed to allow the rest of the device to draw the necessary current, and it's not supposed to degrade the lifetime of the battery too much. Okay, so at 6.2 volts we have 33 microamps and the LED is fully turned off. At voltages between 6.1 and 6.2 we can have some in-between lighting where the LED is not turned off completely, but it's not shining bright. Okay, again, bear in mind that these voltages depend strictly on these two resistors, R38 and R39. I chose them to be around 6 volts for my particular purpose, but you can recalculate them for any purpose whatsoever. Okay, now if we go up in voltage at 9 volts, which is a typical 9-volt battery voltage, when the battery is slightly consumed. When it's brand new, it typically has a little bit more than 9 volts, but as it settles and as you have consumed the battery to some degree, you know, the voltage drops to 9 volts, the nominal voltage. We see that the whole current is about 50 microamps through the entire circuit, and the LED is still turned off as it should be. And at 13 volts, well, not that a 9-volt battery would ever have 13 volts, but just for the sake of, you know, making some tests. Sorry. The whole circuit draws about 73 microamps, again with the LED turned off as it should be. It's still good enough. It's still a good enough current that's not too high, and therefore it's not consuming the battery too much. Now, if we go towards the opposite end of the spectrum at 6 volts, remember the LED was starting to turn on at 6.1, around 6.1 volts. Well, at 6 volts, the LED is turned on even more. We have 3 milliamps going on through the circuit, and we clearly see the LED shining pretty bright. At 4 volts, we have about 2.3 milliamps, and the LED is shining bright enough to be seen. And at 2 volts, which is pretty much the minimum voltage that a LED requires, at least a red or green LED requires to shine light, we have about 200 microamps going through the entire circuit, but it's still good enough for our LED to be slightly turned on. Okay, we still see some light in it. It might not appear so here on the screen, but trust me, the LED is still, you know, it's still lit a little bit. Contrast it with this image where the LED is completely turned off, and you will understand what I'm saying. So basically, this is pretty good, it's working pretty well, and it's a useful circuit that we should have in mind whenever we need to create such a low battery indicator. Okay, so I hope you found it useful. Please hit the like button if you did so. Consider subscribing to my channel as well. I will keep pushing videos here on YouTube. From now on, I will tend to upload videos more towards the end of the month, while in the beginning of the month I will occupy my time with studying and building the things that I will show you. So thanks a lot for watching. Also, if you enjoy this, please consider supporting my work on Patreon. There's a link in the description. By supporting me financially, by helping me to buy components and devices faster, you're helping me to learn new things faster, and therefore I can come faster here on YouTube, make videos and show them to you as well, so that you don't have to spend so much time and energy with the things that you wish to study. You can just take a look at my videos. Thanks a lot for watching. I'll see you in the next video. Bye bye.